Hey y'all, it's Miss Johnson. Finally doing the assignment in the morning so that y'all can do it probably during class, but honestly, during lunch. Cool. So during class today, we talked about exponential functions and how to take their derivatives. I'm going to quickly go over that now. Do some practice problems that look like the assignment. Then you can cut loose and do the assignment yourself. And then you can stay tuned for me doing an optimization problem with this as well, if you want. So just to reiterate from class today, we looked at functions that look like this, like 3 times x to the power 2, or y equals 10 to the power x, or e to the x was the cool one. And we want to know how to take the derivative of those functions. We want to add that to our list of rules that we know just about regular functions. So here's the rule. If you take the derivative of a to the power of x, it's the natural log of whatever a was times a to the power x. And we'll do some examples. So let's just do the first one right now. If your function is 12 to the power x, then your derivative is ln of 12 times 12 to the power x. You basically just recopy the function, but give it a new coefficient. You give it a new number out front. And then we can see exactly what that number would be by plugging natural log of 12 into a calculator. And then, doing the first couple decimals. Great. Right? We can keep going. The one I want to talk about, the special case, is that when you take the derivative of e to the power of x, it is its own derivative. And that's because the natural log of e is just 1. So we plugged it into our rule. We would get 1 times e to the power of x, and 1 times anything is itself. Great. So again, add these to your notes if you haven't already. I'm going to keep them on the side because I always keep my notes to the side when I'm working. You should too. Let's keep going. If we want to take the derivative of something like 4 times 8 to the power x, this is the same thing we do for any derivative. We basically just recopy the coefficient and then take the derivative as normal, not e. Sorry, 8. I think this is a finished question. You can type in 4 times natural log of 8 if you want the decimal version. I don't. That's a personal preference. And so that's the basic ways we use this exponent rule. But of course, we can now, because it's in our list of functions we know the derivatives of, use it in a quotient rule situation, in a product rule situation, or in a train rule situation. Let me do this example as well. If we want to do the derivative of 4 to the power of x divided by 3x squared plus 2x, we are going to equals, I'm going to write out my my pattern for quotient rule. This is what I do every time I do a quotient rule question. Quotient rule pattern. And you might say, Miss Johnson, how was I expected to memorize this? You're not. You have your notes out, right? This is F, this is G, this is G, this is F prime, this is F, this is G prime, and this is G. So when I do the quotient rule, again, first thing I'm going to do is just rewrite all the ones that need to be rewritten for the x, right? In the pattern, these don't have derivatives, so it's just a rewrite. And now I'm going to take my derivatives. The derivative of f is the natural log of 4 times 4x. The derivative of g is 6x plus 2, and I'm done. Right? There's a lot of simplification that could be done. I think this is a finished problem in our class. Nice. Next, we can examine the product rule. So I see that I have two functions multiplied together. I'm going to label one of them f, I'm going to label one of them g. I'm going to do my pattern from my notes for the product rule. I'm going to say this is rewrite f times g prime plus rewrite g times f prime. My first thing I'm immediately going to do is do all my rewrites. Now I'm going to remember the derivatives. The derivative of cotangent is negative cosecant squared. And the derivative of e to the x is just e to the x. Finished problem. I really like math. I've been doing it for like a billion years, so I have all these memorized. I don't expect you to have these memorized, right? This fact and this fact should be looked up on your notes, right? I'm not making you take them because I think they're funny. They're useful. So make your life easier, make things organized, get your note sheet out. And then the last one, we've got the chain rule, because we've got a function inside of another function. So this is chain rule. It's almost cute. We'll call this one G, we'll call this one F. We know that the plan is, this is F prime of G. So we take the derivative of F, but rewrite G. And then multiplied times G prime. The derivative of tangent is secant squared, big parentheses. We just rewrite G. And then we multiply it times the derivative of G, which is natural log of 6 times 6x. Finish question. All right. At this point, you can stop the video. You can do your assignment. You're good for homework. I'm going to do like a fun fact and more problem if you want to stick around. But that's where you can cut it off. Good luck. All right. Hello. I'm sure every single one of you stayed because, wow, math is so fun. I say that as a joke. I do actually mean it. Let's remember about optimizations, right? Whenever we want to optimize functions, we have like a plan. And that plan is take the derivative, set it equal to 0, 0, and solve for x, right? That's all your local maxes and mins. And then we test for if they're maxes or mins. Nice. And we've already got the function. The secret first step is get a function. But we've already got one here, so we're good. So here's the situation. Ms. Johnson is at it again with her fun functions. She's translated her confidence about knowing what's going on in the pandemic to a function, and that function is this function, x squared divided by 2 to the power x. Can you find the local minimum for her understanding of what the heck is going on pre-COVID-19? Find the x value where the local minimum occurs, as well as the y value it reaches. So we have our function. So first step is now take the derivative. This is a quotient rule question, so it's kind of rude, but we're going to do it anyways. We're going to rewrite G on the bottom because that's the easiest one. We're going to rewrite G and multiply it times the derivative of x squared. Then we're going to subtract, rewriting the top and multiplying it times the derivative of the denominator. Bingo bongo. I'm now going to set this equal to 0. All right. We can graph this. We can use the minimum and maximum function on our calculator. I almost said calendar. That's ridiculous. On our calculator and find the x where it works. I'm going to do it by hand just for funsies. I'm going to multiply both sides by 2x to the power of 2. 2 to the power of x to the power of 2, right? And basically this is just going to cancel because when fractions equal 0, it means their numerator equals 0. So we've got 2x times 2x minus boom, boom, boom equals 0. I'm going to do some fun and fancy algebra. I'm going to factor out an x from both sides and factor out a 2 to the power x from both sides. We're going to get 2 minus x natural log of 2. So I got an x over here, I got a 2x, and we're good, right? And now, because I've got three terms equals to, or 3 factors equal to 0, I can set each one equal to 0 to see what x is. So I can set this equal to 0, I can set this equal to 0, and I can set this equal to 0. X equals 0, pretty easy. It's 0, right? 2x equals to 0 never happens. This never happens. And we can remind ourselves what that looks like. When we graph 2 to the power x, there's a horizontal asymptote at x equals, or y equals 0. It never reaches 0. So no factors here. and then the x is confusing. And then when we do 2 minus ln of 2 equals 0, we get that x is equal to 2 divided by the natural log of 2, which is some number. 2 divided by natural log of 2, 2.88539. Boom, boom, boom. Set it equal to 0. Boom. Solve for x's. Nice. And now we just need to see which one of these is the maximum and which one of these is the minimum. If they're both whatever. So we've got our two x's. We've got x equals 0, and we've got x equals this 2.8 number. So over here, I'm going to plug these into the original function. I'm going to say, what is 0 squared over 2 to the power 0? It happens to be 0. Easy. And then I'm going to say, what is 2.8, we'll call it 89 squared over 2 to the power of 2.89. And 2.89 squared divided by 2 to the power of 2.89. It's 1.127. So it looks like this is our minimum. This is our maximum. We scroll up to our word problem and we see what we actually asked. We're asked, find the x value where the local minimum occurs and its y value that it reaches. Boom. So my understanding was at a minimum on day 0 of the pandemic, and my understanding was 0. Makes sense. All right, y'all, that's that for that. I will see you in class on Friday, hilariously, but also today, as far as right now me is concerned. All right, take it easy.